Pauline, thanks for coming on. I really appreciate you taking the time to have a conversation with me. Would you mind telling us a little bit about yourself before we get started?
Yeah. Yes, I'm happy to. Sorry, I have to switch from German in my head to English, and I get stuck sometimes. So, yes, I'm a physicist. I'm a particle physicist. I'm retired since about 9 years now. I was working at CERN, which is the largest physics laboratory, and it's all dedicated to particle physics. That means looking for the smallest constituents of matter. And this lab is located near Geneva in Switzerland, right at the border with France. And so I worked there for about 19 years, and I was doing research. I was associated with Indiana University at Bloomington. The way CERN works, there are about 13,000 physicists working there, people coming from all over the world, and but most people are based in their home institute, and some of us were based at the lab, like myself. So I never worked in Indiana, but I was working at CERN. And so that's where the Higgs boson was discovered. But the biggest discovery of CERN is the World Wide Web. That's probably the best gift to humanity that we had there.
Awesome. And so could you tell me a little bit about the process of how exactly do you go about discovering a new particle?
Oh, that's a long story. It started almost 50 years before. There were a bunch of theorists. Among them, there were Peter Higgs and François Englert and Robert Brout, among others. And they were interested in solving some problems that we had at a theoretical level. And the problem was that all the equations that we had to describe particles, fundamental constituents of matter, all those equations were giving massless particles. But we knew that the particles that we were seeing in the laboratory and around us had a mass. So they had to find a way to introduce mass. And in doing that, they had to reshuffle the equations and all that. And all of a sudden, they found a mechanism, but this mechanism meant that there would be a new particle associated with it. So they predicted that in the 60s. And so those were a bunch of theorists, and there were lots of other people before them who had brought various pieces to that theoretical concept. And so they had foreseen that there would be a new particle, and this particle is now known as the Higgs boson, because Peter Higgs was the first one to mention that there would be a new particle with the field that they had discovered. And so they said, yeah, it should be there. Could you look for it? And so it's not an easy one, because it's like I'm sending you on a hunt, and you're going to hunt for some animal of some sort, but you have no idea the size of it, what it eats, what it does during the winter or whatever. You have no idea how you could catch this animal. So that's what we did then, was to set all sorts of traps, large ones, small ones, for vegetarians, for meat eaters, for those who like sweets and nuts. So we had various things. So the way we did was to look at just about every possibility that different theorists would put out for us. And then we had to go and look for possible signs of this particle. The way we do that is that we have two main tools. The first one is the accelerator, and the second one is the detector. And the accelerator is there at CERN, the lab where I was near Geneva. The accelerator is 27 kilometers around. That's about 17 miles around. It's a tunnel. It looks like a subway tunnel. And it's about 300 feet underground to protect from radiation protect the people from radiation, but also to avoid having cosmic rays hitting our particles and just mixing things up. So we have this accelerator, and in this accelerator, we accelerate protons at near the speed of light, and we bring them in collisions right there at some point. And we hope that out of this collision, lots of energy will come out of it, and this energy will materialize into something else. And it's something else can be just about anything. And it's just like with playing with the Play-Doh. If you start with a little bit of energy, you can create light particles. But if you have a lot of energy, you can create bigger ones. So since people had been doing all sorts of experiments for a long time, we knew that the Higgs boson had to be fairly heavy, because when we were producing lighter particles, we didn't see it. So we were looking for a particle with very specific properties that they had described. And so we had the accelerators to try to produce this new particle. But then the second tool we have is the detector. And the detector is a huge apparatus made of several layers. It has the shape, the geometry of a tin can. And so you have a barrel and end caps. And so we have several layers of detectors, and those detectors will detect when a particle, some fragments or particles will fly through it. So what we do, we produce large, heavy, unstable particles, and those will decay, they break apart, and there are fragments flying in all directions. Those fragments are more stable particles like electrons or protons or neutrons or pions or kaons, various things that we know very well. And we have several, the detector is made of several layers, and each layer is able to tell us something about those particles. If they had an electric charge, if it was positive or negative, the speed at which they were flying apart, where they came from, if and different properties of the particles. And they leave tracks in our detectors, just like animals would leave tracks in fresh snow. So if you're a hunter and you're looking for a new type of animal, you can look at the tracks that you see in your detector, and you can tell, that was an electron flying out here, or proton, or photon, or various particles. And we take all the fragments and we try to rebuild what was the original unstable particle that was created in our detector. So I go again. So we have this huge accelerator, 17 miles around. So it's a huge circle. I should do it in this direction. And we have protons going in both directions, circulating at near the speed of light. They collide. Out of this energy, the energy will materialize, and it will produce something, new particles. They're very unstable, like the Higgs boson lasts 10 to the minus 25 seconds. So it's 0.000002401 second. So you have to be goddamn fast to catch them. So we catch them from their tracks that they leave in the detector, just like animals would leave tracks in the snow. And it's just as easy as interpreting the tracks that you find in fresh snow, because the particles leave very different signals in the different layers of our detectors. So, and then by comparing that, we can easily tell the difference between them. Just like it's easy to tell the difference between a squirrel, a deer, and a skier. It's just as easy as that. And so we were looking for typical things that would be a sign of a Higgs boson. So the Higgs boson, one possibility was that it would decay into two Z bosons, and then the Z boson would decay into electrons or muons, and we would see those electrons and muons flying through the detectors. And that was a fairly clear signal: 4 electrons or 4 muons flying out at a high speed out of the detector. So those are quite striking signatures, and that's what we're looking for. And the trick in particle physics is that everything is based on statistics. So it's not like, you catch one and you say, that's it. Here I have a picture of a Higgs boson. But that's not what we do. What we do, we have to compare how many times would we find events, so pictures that we get of those uh, particles exploding, just like mini fireworks in the detector. How many times would we see uh, 4 electrons or 4 muons coming out from other things that we know outside the Higgs boson? And there are all sorts of possibilities. And what we had to do was to look, did we find more of those events than what would be produced by other well-known phenomena? So it took a lot of time to accumulate enough data to see indeed that there was an excess of those events being produced. And then we could tell that, yes, there was a Higgs boson because there was this excess of events being created, and they were all piling up at the same with the same mass for the original particle, and so we knew it was all coming from Higgs bosons. And then we had a party.
So what is the material that you use to detect the particles? Like you say, they leave tracks. They leave tracks in what? What is it that they're interacting with that is detectable in such a way that you can
Yeah,
measure
so
them?
they're very all sorts of different technologies. Some of them are pixels, like you have in cameras now. All your phones, mobile phones, the cameras that you have, they're pixels. And when there is either a light coming or some particles, they will just generate a little signal, and we know that something went through it. And then we just connect the dots. We have several layers of those pixels, and then we connect the dots, and we can tell, one particle flew this way, things like that. Another type is with the silicon detectors, and they're also very precise. The type of detector that I was working on was called a transition radiation tracker. It had 2 roles. First, to detect the particles, but also tell us about what the type of particle that was doing it. But that never worked too well. But the rest is a very conventional gas detector. So we had long straws of about 4 feet long, filled with a gas. And when a particle with an electric charge goes through this gas, it will ionize the gas. So ionize the gas, it means that neutral atoms will lose electrons, and you will have an charged ion left behind. So then the electron, if you put a potential difference between the straw and there was a little wire the size of a hair inside. So we had a tiny straw, the size of a normal straw, but 4 feet long, with a wire inside. And there were about 1500 volts between the wire and the straw. And then when a charged particle goes through the gas, it ionizes the gas. The electrons will drift to the wire, and then we get a little pulse on the electronic device that is attached to that straw. Then we can tell, this straw was hit. And we had several layers of straws, and then again, we connect the dots, and we can track the particles this way. So that's the type of techniques that we use. But all the techniques that we use, at the beginning of particle physics, they were mostly using emulsion, like pictures, like film, negatives. And later on, things that are more like digital electronics to record all the events, because now we are becoming too many of those events in a second, so we could not do that. Yeah, we're getting hundreds of thousands of pictures at a second, so it's a very large rate. And then we have to we take a lot of those pictures, just like a tourist in the vacation. You take lots of pictures, then you go home and you sort them out. But it's still a huge job to sort out through all those pictures because we take so many of them. And it's even though we have some minimal criteria to start with, not to take everything, but at least having one something that looks interesting in it, then we start from there.
And how do you differentiate the critical information from just noise? How do you tell this is definitely a new particle?
That's a big job. This is we were using for that often techniques that are now used in intelligence, artificial intelligence, and so we've been using those techniques now used in uh, artificial intelligence for a long time in particle physics. So essentially, what we were doing, we would try to compare, we would try to predict what any the events that we are interested in would look like. Using that, we were using simulations. So we would simulate the passage of all the particles coming out from the decay of a Higgs boson. We would track them in the detector and simulate what would be the response of our detector. But our detector has something like 200 million channels, so it's a lot of a job to do all that. So we do that. We do simulations of events, and we simulate millions of those events, and then we know what they should look like. As I mentioned earlier, in particle physics, everything is based on statistics. So we need we need a lot of events to get the general behavior, what should it look like. So what we did then, we would generate events that look like what we like, and events that would look like noise, background noise, or events that are the riffraff type of events, no events that are very common, very well known. No, we got Nobel prizes for those discovery 20 years ago, but now there's just junk that gets in our way because they are masking more interesting, newer type of phenomena. So what we do, we simulate all the type of events that we think we will see in our detector. So for that, we have to rely on what theorists predict, and then accurate simulation of how our detector will react to all those particles. And we always test that our simulations are really uh, matching exactly what we see in the detector, under various conditions. And then we know what it should look like, and we know what the noise should look like. So we can easily put criteria to differentiate the two. For example, here we can say we need to have minimum five high high speed flying particles coming out of the same vertex, for example. Or we need to have at least two electrons or two muons in that event. And so then you can adjust we do all of what we call our analysis, or we develop the criteria to select our events based on Monte Carlo. And when we're really sure that it works well, then we apply it on the data and we see what it does. The whole thing is not to get biased. So you don't want to look at the data before you have established, okay, these are the selection criteria that I have and that I will use to select my events. And you don't want to mix, and it's very difficult. And even the most honest physicists you can find, like myself, you get tricked. Like sometimes, like I was looking for some events, and I knew I should find something like 25, and I saw that when I was applying my cuts in such way, whoops, I was getting 25. And then for another situation, I was supposed to get 33, and again I got 33. But in fact, I was just selecting my criteria just to get what I wanted, and even without realizing it, it's really pernicious. And so I was working really late, thinking I would find this thing, but then I realized no, I was completely biasing my sample, and so looking at the data is very dangerous. You have to do it at the last minute. It's the only way to do it in a safe way. So, and with the large collaborations that we have now on the Atlas experiment where I was at CERN, there are about 5,000 physicists working on it. So it's a lot of people. And so we have lots of people looking at different ways and all that, and you always cross-check each other. And at CERN, in fact, before we could claim the discovery of the Higgs boson, we had two different experiments, two different detectors, two groups of about 4,000 physicists on each, doing different ways, different technology, different detectors, and we found the same thing. So we could tell it was good.
And what do you think are like the biggest challenges in doing these kinds of discoveries? Because when the information comes out, is it essentially just a bunch of numbers, mathematical numbers that you have to put into a calculation? Do you get like a visual representation? What is it, the method by which you can see this information represented?
We can look at the events, we can look at the pictures themselves taken in the detector, seeing where all the fragments flew apart, and with each track being identified and all that. But usually we look at, when we do histograms, that is, we do distributions of what it looks like for the energy of all the particles that we have found in that type of event, and we see if these looked like what we were expecting or not. And we usually, for events coming from the Higgs boson, they will have a lot of energy, whereas the background, which will be all sort of random low energy collisions. Sometimes to produce the Higgs boson, we needed very head-on collisions, but they're often collisions where they're just grazing, and then you get much less energy being exchanged. And so what we do is usually looking at distributions of events and a number of events passing everything. But normally we look at distributions of the energy, the momentum of all these particles, the number of particles found, in which direction they were flying, all sort of things like that, that we look to make sure that everything looks like what we were expecting. We spend hours and hours doing it, redoing it, redoing it. It's refining, defining. It's tedious, and of course, because we have accumulated billions of events, it's huge amount of data, gigabytes and terabytes that we need to process. So it's high
A lot
tech,
of work.
lots of work, yes, and
Are
it's
there any?
tedious. Yeah.
Have you ever gotten any unexpected results? Things that you were not in any way expecting in your experiments?
Um, there are always things that look really weird, and sometimes you can find an explanation for it, and sometimes you don't. But out of billions of events, you always find a couple weirdos that you cannot put in any category that you know. And so there are always a handful of those events lying around that people are trying to understand and interpret. And right now, not in Atlas, but the other experiments, CMS at CERN, they have a few of those events that look like a new boson, but it's too few events to be able to say anything about it. So until they find more, and until Atlas also finds a few of those, we won't be able to tell anything. But finding something that would be highly unexpected, it has happened, yes, in the history of particle physics, but not in the history of the at CERN with the Large Hadron Collider. There, so far, no, things were all things that we expected, and there's nothing that has been so
Gotcha.
there, I see some comments passing by. We just okay, okay, it's something else.
Yeah, they're yelling at each other in the chat, having internal arguments. Um,
Okay, okay.
do you think we're going to need a more powerful collider to make the next real big discoveries in particle physics?
Right now we're kind of stuck. theorists, we know we know that with the Higgs boson, everything that the theoretical model that we have to describe particle physics, this model is called the standard model. And every particle in the standard model seems to have been found now. And we have a complete theory in all that. But the problem is that the particles contained in the standard model, it only explain 5% of the content of the universe. As you probably know, there is also dark matter, which accounts for about 25%, 27% of the content of the universe. We know this matter is there. It's called dark matter because it does not emit light like all the stars that we see around. And there would be about 5 times more matter than the sum of all the stars and galaxies that we see out there. So it's really problematic. Uh, to only understand 5% is bothersome. The rest, so we have also dark matter, which would be about 27%, and we have about 68% of the content of the universe is in the form of a type of energy, which is called dark energy, to go with dark matter. So it's a type of energy that we have no idea what it is. We know it's there, and the reason for it is that you know that there was the Big Bang, and since the Big Bang, the universe has been expanding. But about 20 years ago, it has been proven by two researchers from Stanford, and I won't remember the names now, but it has been proven that not only it's expanding, but this expansion goes accelerating. So the expansion of the universe is constantly increasing. And you know that if you want to accelerate when you're driving your car or if you're running, you need to give energy. So you can imagine that to accelerate the expansion of the universe, you need a lot of energy. And so we see that there is a lot of energy out there that we have no idea what it is, but we need about 68% of the whole content of the universe to do it. And we know those number of 5% of regular matter, all the matter you see here on Earth, as well as in stars and galaxies, that accounts for 5%. Then 27% is dark matter and 68% is dark energy. How do we know that? It's from simulations from cosmology. You can try to recreate what happened after the Big Bang, and you put tons of particles at the beginning and let them evolve with computer simulations, and you give them 20 billion years to evolve in accelerated, of course, in the computer program, to see how it goes. And you want that after 20 billion years, you want it to look like what we see out there with telescopes. And the only way this works is if you put dark matter and dark energy. And the amount that you must put is 27% dark matter and 68% dark energy. It is as if you're making a cake. And you know that to make a cake, you need some milk, some eggs, flour, sugar, bit of butter, but most importantly, you need a rising agent. If you don't put any yeast or was not going to, I never bake, so I don't know. But if you don't use a rising agent, your cake won't rise. And it's the same with the universe. If you don't put dark matter, you will not be able to get galaxies to form as early as they did in our universe. So it's an essential ingredient for the development of the universe. So without dark matter, you don't get galaxies to form as early as they did. And it's easy to understand because dark matter is a form of matter that doesn't emit light, but it produces gravitational force, gravitational attraction. And since there is no electric repulsion due to electric charges, then it's easier for this matter to coalesce and to start forming small seeds where more matter will be attracted under the gravitational force, and eventually it will do like a snowball effect and it grows. And so that's about what happened. And so without dark matter, it would not have happened as fast as it did. So with some supercomputers, those simulations have been done, and they prove that you need that. And there are also measurements that are done with the cosmological background. And this is something, cosmologic microwave background is some sort of background noise that you get if you take an antenna that is sensitive to microwave waves. You will hear that noise coming from everywhere in the universe. It corresponds to the light that was emitted at the beginning of the universe that is not traveling, but since the universe has expanded, this light, which was invisible light when it was emitted, the wavelengths have been stretched. And now the wavelengths are much longer and they correspond to microwave. So there is this background of microwave radiation that is coming from everywhere, no punctual source, but everywhere in the universe. And if you look at this cosmological microwave background, you see that the only way to reproduce the distribution of the objects that you see is, again, by adding dark matter. So dark matter, we don't see it, but we feel it. We know it's there. And you also see it with gravitational lensing. That's another way.
So Tim West has a question about that. Thank you for the super chat. He says, question for Pauline, why do we assume dark matter will fix the problem? Isn't it more plausible that we just don't have a complete understanding of gravity? No WIMPs have been found so far.
Yeah. I'm not a cosmologist and I'm not a theorist working on those things. I'm an experimentalist. But from all the discussions I've had with theorists and cosmologists is that this thing of modified gravitation doesn't bail out. It doesn't work. It's not only a question of not understanding gravity, but it's way more than that. We see dark matter, the need for dark matter in many different ways. As I said, in the formation of galaxy, explaining the distribution of the cosmological microwave background, explaining, we see it through gravitational lensing. So it's seen in different ways. It's not just one thing. It's in many different areas that you realize that there is a dark matter. And so this modified theory, very, very few people believe in it. It's all, but I agree with you. You don't see it, you don't smell it, you don't, but it really is a sound theory because it's come from 3-4 different areas that we have proofs for it. So it's quite compelling. It would be very difficult to go without.
Peabot Thulu asked another question. He says, what might the next undiscovered particle be? Because if the Higgs is mass, what else could possibly be discovered? Because the mass seems to encompass everything.
The Higgs is not mass. What the theorists did was they said there is another field of force that is there that permeates the whole universe, and when other particles interact with it, they gain mass. And the Higgs boson is simply a wave on that of that special field. It's just a manifestation of the field. It would be maybe a bit longer to get into that, but the next thing we might find, that's the big question. That's not a $10 question. It's a bit more than that. As I was saying earlier, is that we are stuck right now in particle physics because we don't have any evidence for something in which direction we should go for what is the next thing that will be found. We don't know. So that will come as a surprise, what we will find. And we're looking for different ways. We're looking for new particles by testing all sorts of hypotheses, but we're also looking for anomalies. The standard model, this theoretical model that we currently have, makes very, very precise predictions. And we can test some of them up to the fifth decimal. And we haven't found, not fifth, sorry, ninth decimal. And so it's extremely precise. And so we are checking all sorts of very rare phenomena, hoping that we will find a small deviation from what is predicted. And then we will think, what could create a perturbation here? And then we can maybe think, or some theorists might be able to imagine what kind of a particle would do that, and then we can look for it. So right now, we don't know which one would be the best. We don't have enough experimental constraint to tell us that there are dozens of theories out there, and we cannot tell if any of them is right or wrong. All of them are plausible, but we don't know if any of them is valid or if they're all wrong. We need an experimental discovery, but up to now, we don't have anything. So it's a difficult time. So if something new was there, we were thinking that it would jump at our face, but nothing new was found. It's like we landed on the moon, and we were hoping to see maybe little funny creatures, but we didn't find them. So now we're looking. We're just we're trying not to leave any stone unturned. We're checking every single possibility, and we're mostly looking for anomalies and deviations in some precise measurements, predictions, such that we could maybe find a clue, a hint of what could be next. So it's a difficult time. So, and if we do not find anything, yes, if we want to go further, we might need a bigger accelerator to do it. Right now, the plan for the LHCs, we're not going at higher energy. We're staying, we're at the limit of what it can do. So we cannot create larger particle, but we can produce way more of them. So now it's in the fine prints that we are looking. We're looking for small anomalies that at the 10, 12, 15th decimal. So for that, we need huge amounts of events. And it's not easy. I worked on this for about 20 years on the people worked on Atlas for about 20 years to build the detector and run the experiment and all that before we found it. But we found the Higgs boson in 2012, and that was 48 years after it had been proposed. And so it's you have to be patient. It's not an easy task. And if there had been something like supersymmetry, we were hoping supersymmetry would just jump to our face. New particles would just appear in the detector. That did not materialize. So supersymmetry is not ruled out, but it's becoming less and less likely. And what we were expecting didn't turn out. And the Higgs boson was so run-of-the-mill. It didn't have any particular aspect that would give us a clue for something else. It's just as bland as can be. It was the most boring boson we could find. Yeah, unfortunately, it didn't bring anything new. It confirmed something that had been predicted, and that was amazingly wonderful to do that. But it didn't bring any clue for where to go next. So right now, we're stuck because we have no clue which theory among the numerous theories that have been predicted is right. There was a couple years ago, right at just before CERN closes in December, on the 10th of December, before the Christmas break. There's always a big meeting where all the experiments show the best of what they have found during the year. And on that meeting, they presented both Atlas and CMS presented, a small excess of event, and exactly at the same place. It was at 450 GeV, the mass, and it was 2 photons seeming to come from a new particle with a mass of 450 GeV. So that's about 450 protons. So just to give you a size. And the Higgs boson is only 125 GeV in comparison. And so that was really weird because 2 experiments people had not been talking to each other, except if a couple of them got drunk in a bar somewhere, in the same bar. But people had not been talking to each other, were using different techniques. Both of them were seeing the same thing. And it was just before the Christmas break. Everybody had a ruined Christmas vacation that year because everybody was trying to recheck everything. But between the December and April, generally, the accelerator is stopped, and we do some major maintenance. And imagine 17 miles of high technology, there is always something that fails. And so we need to do major maintenance once a year. So the accelerator was stopped for a few months. We had just found that. And so everybody refined their analysis and all that. And we were all ready when the new data started coming and everybody was looking at it. And when we looked, we had defined our criteria really tightly without looking at the new data. And just a few days before the major conference on August 1st, then people looked at the data and there was nothing. It was just bad luck that there was this statistical fluctuation in the data. But meanwhile, there were more than 350 theory papers that had been published between December, the 10th of December, and the 1st of August. And even a few more afterwards. Some people just couldn't let go of the idea and those theories, they were all sorts of theories. All of them, most of them, I would say 90% of them were valid, were plausible, but nobody can tell which one is good and if any of them is good. We need an experimental discovery for that. So that's why we're stuck. Until we find something, we cannot go any further. I doubt that theorists can do any more than they have done now. Well, there are a few intriguing events in the data from CMS, the other experiment. And so, the accelerator will restart a little later and will run a little less this year because of lack of energy due to the war in Ukraine and the problems with energy in Europe. And so CERN is also affected by that because they consume a lot of energy, and we're all freezing here this winter. So and drinking lots of tea. So everybody has to make an effort. Yeah.
Yep. Peabot Thulu asks, could you unpack supersymmetry for us lay folks?
Yes. Supersymmetry was people love symmetry in physics because symmetries are always associated with very specific laws in physics. That was discovered by Noether, Emily Noether, theorist. I can't remember where she was from, but anyway, she always showed that with every conservation law there was symmetry was conserved, and so it brought
Noether's theorem, right? Noether's theorem.
Sorry.
Noether's theorem. That's the
Noether's theorem. Yeah. So Emily Noether did that. So supersymmetry was something to try to bring together two types of particles that are described by the standard model. The standard model has two types of particles. There are particles of matter, and those are called fermions, and there are particles associated with forces, and those are called bosons. I keep talking about the Higgs boson, and it's just a family name. I'm a Gagnon, and they are bosons. It's just a family name. And so fermions all have a spin that is 1/2, whereas bosons have spin, so a quantity of intrinsic magnetic moment. No, not kinetic moment. That is an integer. And so it's kind of strange that there are, and the two types of particles, if you have a spin 1/2 or a spin 0 or 1, those particles will will obey very different laws in physics. So it's kind of strange that there are particles of matter, particles of forces, and they obey different rules. And so some people thought, oh, it would be nice if we could bring them together somehow. And that's how the ideas of supersymmetries were brought, or that's the way I understand it. And the idea was that each particle of matter would be associated a particle of force, and each particle of force would be associated a particle of matter. And so it created way more new particles that would come, and it would solve all sorts of difficulties, theoretical problems that I'm not really good at explaining. So, but this theory was very popular, this idea of supersymmetry, because it brought more harmony between the equations. And for some reason, physicists, astronomers are the same. They love harmony, that things are simple and all that. Like, for the longest time, astronomers were convinced that all the planets' orbits had to be perfectly circular because a circle was perfect and all that. But it was not so. It was ellipses. Okay, so supersymmetry came like that it would solve some problems of the standard model. And some particles that come, new particles that come with supersymmetry, would be perfect candidates for dark matter. So the biggest question these days in particle physics is to figure out what is dark matter. We know that the regular matter is made of particles. So we think maybe dark matter is also made of particles. And so we're looking for particles that could fit the bill, that would have the properties that we see for dark matter. And but so far we haven't found it. There are all sorts of hints here and there, but nothing has built out so far. So supersymmetry was a theory that was invented just to bring more symmetry between the two types of particles contained in the standard model. And it had this wonderful side effect of coming with particles that would be perfect to explain what is dark matter. So it got very popular. There is only one major problem, is that we haven't found any of them. There would be tons of those particles and none has been found. And we theorists thought that they would be fairly easy to find within the reach of the Large Hadron Collider. So it's a bit surprising that we haven't found it. So it seems it's not yet ruled out, but it's not as favored as it once was.
Gotcha. Winston's mom asks, question for Dr. Gagnon. What questions nags at you, and what questions would you like to find the answer to?
Dark matter. Dark matter, of course, is the big one. When I was a child, I used to say that I wanted to know what matter is made of, and now we know. We found it. We found the last particle that was missing, so I'm happy. But we just realized that there is 5 times more of another type of matter, and there we have absolutely no idea what it is. So it's it's bothersome. So that's the question that I'm the most interested in, and I would say that a very large fraction of particle physicists right now and astronomers are just obsessed by it.
Do you think we're going to discover any more forces that are 40 orders of magnitude weaker than gravity?
Better get up early, but 40 orders of magnitude lighter than gravity, I tell you, you don't have much left. Gravity is already very light, so no clue. Some people talk about extra dimensions. There are all sort of possibilities on the table, but again, no, all those are still plausible. Nothing that we have measured rules them out, but we cannot rule out dozens of theories. So it's a bit annoying because we haven't found anything yet. We need an experimental. The ball is really in the camp of experimentalists. The way it goes, usually, theorists make some progress based on recent discoveries, and then they formulate ideas and all that. We test things, whoop, we find something else, and they come back with something, a new development, and we check that if it's right or not. But not the ball is in our camp. We need to find something. But so far, we haven't been lucky. And I'm glad I'm retired because it's a long haul. I think we're in for a long haul, but the prize is huge. We have explained 5% of the content of the universe. 27% is there to be explained. So for those students who are starting, it's very exciting that this huge thing that is passing by us, and we have no clue what it is. Yeah.
Surrounded by Keith asks, is dark matter really there, or is it just filling a gap in our equations?
No, it's really there. It's really there. The most direct view, I guess, there are two that I can think of quick. It's with the gravitational lensing. Like I said, so we see that there is way more matter distorting the path of light. So you look at some stars, you know where they are, and whoops, all of a sudden they appear to be displaced, as if there was a lens being placed in between a huge amount of matter that will distort the curvature of the universe, and they will go elsewhere, those rays of light. So that is there. And the second one is with the rotational galaxies. There are some galaxies that spin on themselves, and it's like a merry-go-round. If you put your child on a merry-go-round, you tell him or her, hold on fast, because you know that they will be ejected once that it starts to spin. So stars within a galaxy would also be ejected unless they are held by a force, which is not their hands gripping on the bar, but the gravitational attraction to the center of the galaxy. And it's clear that those galaxies are spinning way too fast, and the stars would be scattering around. If there was only the amount of matter that we see coming from the stars that we see within the galaxies, and so you need way more matter inside those galaxies to provide the necessary gravitational pull to hold the galaxies together. And this was proven it was first observed by a Swiss astronomer, Fritz Zwicky, in the early 1900s. And it was proven by Vera Rubin, an American astronomer. She died about 3 or 4 years ago, and she was never offered the Nobel Prize, but she highly, highly deserved it, because she brought the first solid proof of the existence of dark matter. So those are not theory, they are facts. Those galaxies would just scatter all their stars if it was not for the extra gravitational pull provided by the dark matter.
Gotcha.
So this is solid.
For sure. Gmul asks, "What are there any other novel predictions that have been confirmed by CERN?"
Oh, tons of small things that that the coupling between this particle and the other one, how attracted they are to each other, and we calculated that, and it goes smack on. But who cares, in the general public? There's hundreds of measurements being made every year at CERN that are confirming with increasing precision different predictions that have been done with the standard model. So the theorists are refining their predictions with better techniques, better computers and all that. And experimentalists, we're refining our measurements as well. So yes, there are tons, but nothing that is earth-shattering like the discovery of a new particle that proved that there was a new field of force that was providing the mass to all particles.
Mr. Crean asks, "Doesn't Bose condensate and interstellar gas add to the missing dark matter in addition to neutrinos?"
Oh, God. Bose with an S. It comes from a Indian physicist. His name was Bose, and a Bose condensate. I was saying earlier that bosons and fermions, particles of with integer spin, act differently, and so bosons you can the merrier. So you can put as many boson as you want in the same position, but you can only put two fermions, like two electrons, in the same position, and they have to have opposite spins, and there's just two positions. You can only put one fermion in one particular state. So on the hydrogen atom or any atom, you can only put two electrons, one with the spin up, one with the spin down, in one particular atomic level, because otherwise it violates those laws for what are called Bose-Einstein statistics. Bose did all the calculations, but he associated himself with Einstein, just that it would get more of a recognition, and it did. But Bose, the one who did all the calculations there was mostly this Indian physicist. So does a Bose condensate interstellar gas add that missing dark matter? Neutrinos cannot do the tricks. That has been proven. I don't know.
All right.
Well, we can always string lots of fancy words together and say yes or no. I just don't know.
Fox Rotter asks, "Why is it hard to explain gravity at the quantum level?"
No clue, but I just know that it's terribly hard, and everybody has failed to do it so far. Those two theories don't seem to go together. So that's so many people. Albert Einstein was one of them who tried to explain to unify all the forces together, but it has proven extremely difficult. And I don't know. I'm not, I'm not a theorist, and so that's not the kind of things I do every day. But it's just very tough. I don't know.
All right. We have one last question from Mr. Creening. "How are we not moving towards an anti-de Sitter space cosmology, given the Schwarzschild radius constants, and how do you interpret the holographic principle?"
I'm a frozen fuzzball person. Okay. How about you? Yeah, I feel like it too, reading your question. This is a string of fancy words again that, I'm not into science fiction, but particle physics has nothing to envy to science fiction. What we come up with, the theories that are on the table are that kind of things here. But no, I don't know any of the specifics of that one.
Gotcha. All right, we have been going for. Go
This
ahead.
probably comes from someone who reads tons of those popular science books and then gets all sort of good ideas.
Awesome. Well, we have been going for an hour, and you said you didn't want an hour limit. I really appreciate you coming on. It was a great conversation. Do you want to give any links or references where people can find out more about your work?
Yeah, I guess the best thing, if you're interested in finding out how particle physics works, where we are right now, everything about the dark matter, the proofs that we have, and all that, and where we might go next, you might be interested in my book, Who Cares About Particle Physics? So everything about CERN, the Large Hadron Collider, and the Higgs boson. So you'll get the experimentalist vision of how it goes. How do we find those particles, and what do we do with them, and how it works. And also you will learn about how particle physicists work in terms of groups in experiments. As I said, we're about 5,000 people now, and nobody gives orders. We all decide, we're all free to do what we want. And the funny thing is that it works. And we did find the Higgs boson, but everybody is free to act as they want. And I also address one very important question, is that all that costs a lot of money, but the spin-offs from particle physics are huge, especially, I mentioned the World Wide Web. This is a tool that we needed to exchange information between scientists coming from all over the world to work on those projects. Most of them are in their home institute, so we needed a tool to exchange information, but also in all that you have, the development in the telecommunications and electronics, computers, all that stem from initial research on electrons and electromagnetic waves and all those things, and brilliant engineers and technicians who managed to put that into some use. So, and medical imaging is the biggest spin-off from particle physics. Lots of technologies are used in imaging. Anyway, if you want to learn more about particle physics here, I highly recommend my book. I tell you, it's the best book on particle physics I've ever written, so I highly recommend it.
Yeah. Awesome. Thanks again. I really appreciate it. I hope you have a wonderful rest of your day.
You too. Okay. Thank you for inviting me here. Thank you. Absolutely. For listening.
Talk to you.